Well, now let's try and figure out, and this is impossible again, the size of the universe. Somehow we can figure out. It's been, like I said, everything's moving. The universe is expanding. And so the question becomes, this is part of Hubble's law, that everything's moving apart. So how big is it? And it's expanding. How big is it going to be? Is it going to go out and stop expanding? Or is it going to get out and stop and then fall back and collapse and then do it again? So there's lots of people out there trying to answer that question. I think the prevailing theory is it's just going to keep going and never go back to fall back in. But it's, we've been, I think at the top here, we're thinking this from here to here right now is around 100 billion light years across. That's quite a size to it. So when I say no bang, it means no noise. In space, there's no noise. That's not true. We have radio telescopes that can look and hear at radio frequencies, and we turn that down to something we can hear, and so there's noise. But everything we see out there is on a spectrum, and so we can see light for just a small part of the spectrum that we can see. Bees and things can see more. We'll talk about that. But it does make a bang of a sort. We're going to take this to a little bit extreme. If we boil down a light year into the size of a grain of sand, if we start looking at it from that perspective, how many grains of sand would we need to get across the universe? Okay, this is just for exercise shape. So somebody estimated that there were 7.5 quintillion, and I don't even know, I had to look that up to see how big that is, grains of sand on all the beaches of all the world. That's a lot of sand, by the way. So the question becomes, how much sand would we need? How many beaches of sand do you think we would need? So I've got a picture here for somebody who wants to guess, and I'm not expecting the right answer, so. 20? 20. So 20 is the answer. So we need 20 beaches of sand, right? That's what we're thinking? Okay, so how many earthfuls of sand would we need? Since we got that answer, let's go ahead and, so we've got 20 beaches, but now let's turn it up to the scale of how many earths is full of sand would we need. So I'll let somebody else guess. So your 20 is just a little low, but you get a picture here for that someplace. You're on number 11. A million? 100,000. All right, so let's see how many we need here. 120,000 earths full of beaches full of all the sand on 120,000 earths to do that. That's a lot. And the real question becomes, so there's an actual calculation here I did right there. So plus or minus 2 or 3 miles. I'm sure it was off by a couple. Now, the universe is expanding. So every day you'd have to throw on another beach because it's expanding so fast that you'd have to throw on another beach just about every day to keep up with it. Expanding. So let's go ahead and take a look at the Milky Way, which when you look up, looks like grains of sand. So that kind of looks like grains of sand, doesn't it? So each one of those is a star? No. Each one of those is a galaxy. All of them. 10,000, they estimated 10,000 galaxies in this picture. And if you're to take that grain of sand and hold it up in the air, that's the size of the piece of sky that they're looking at. They found the darkest spot in the sky that they could find, and they looked at that for, what did it say, 11 days at night. Every night they took pictures of it, and this would cover this entire chart if you held it in the sky. And there is they counted 10,000 galaxies. Each one in there has anywhere from 100 to a trillion stars. So that's a lot. You can see that this is what a spiral galaxy. You can start, when you start digging in and looking, you can see some of these that look like this are just turned sideways. That's just sideways you can see. Now the next, who did an experiment in high school or even elementary school, where you made a little model of the universe and all the little planets went around the sun. Somebody had to do it. Hit this lady in the back there. Did you do one? So this is a butterfly nebula here for you on number 9. Did you get a good grade on that? Just for heck? No. This is why you became a, what'd you become? HR. This is why she now works in HR, not astronomy. So I look at something like this, and this is the model that we were taught. Everything kind of rolls around each other, looks pretty cool, and for most part, nobody needs any more unless you start doing some orbital mechanics or decide you want to go in a spaceship for 10,000 years and try and get to Alpha Centauri that's not there anymore, that's been moving every time you're going there. All right, so everything is moving around each other. So does the moon orbit the Earth? Yes or no? No. Sorry, doesn't. The Earth and the moon orbit each other, and they go around the sun. So this picture is actually still wrong. As the moon goes by, it's pulling on the Earth. We know that because of the tides, and it actually wobbles back and forth. And here's a picture of what Jupiter and Saturn do to the sun. This is the center point of the whole rotational system. And they're actually pulling the sun away from that center of rotation point. So nothing is, when you talk about something orbit, and they got to figure this out when they launch payloads into space, that everything's moving. You got to know that. You don't need to know that to do most of the jobs that we do. But that's what's happening with just the impact of Jupiter and Saturn. But you've got all the other smaller planets in there, and Jupiter is yanking on all those as well. So these aren't going in a straight circle either. The sun is also pulling them off, and they're on elliptical orbits. They're not on round orbits. So there's all kinds of stuff going on. And then all that is flying around the sun that's moving through our galaxy. So this gets quite complicated, and if you haven't shorted out yet, then I'm going to keep going, and we'll finish this short. So this is a rendering of our galaxy, and this is the path that our actual sun is kind of taking. I don't think they've actually measured, because this is like a thick $60 million wobble trail through here, but even our sun is wobbling around, and everything in here is moving. So what we see and what we've been taught is a little different. Does it matter? No, unless you're doing some astronomy and start looking for stuff, and then you start worrying about this stuff, which causes me headaches.